Welcome to episode 124, Spotlight, Information Input Validation, focusing on Control SI-10. In today's interconnected systems, hostile inputs are not exceptions, they are normal conditions. Every field, file, or API request must be treated as potentially malicious until proven otherwise. Attackers exploit unchecked inputs to inject commands, overflow buffers, or corrupt data, transforming routine interfaces into entry points. Input validation stands as the first wall against those attempts, shaping data into safe, expected forms before it interacts with trusted logic. When validation becomes habitual, systems gain resilience not by reacting to threats, but by rejecting them outright at the door. From there, inputs that failed checks should be rejected, sanitized, or encoded consistently to prevent secondary harm. Rejection discards dangerous data outright. Sanitization cleans but keeps essential content. Encoding transforms input so that potentially harmful characters lose power. For example, encoding user comments before displaying them on a web page neutralizes cross-site scripting attempts without silencing legitimate input. Consistency is key. Mixing different strategies across modules breeds gaps. Centralizing sanitization logic or using standard libraries ensures uniform defense. When applications apply predictable rules every time, attackers lose the ambiguity they depend on to slip through. Allow lists outperform ad hoc filters because they define what is explicitly allowed rather than trying to block every conceivable threat. Blocking bad patterns is endless. Allowing only known good ones is finite and enforceable. For instance, accepting only alphabetic input for a name field or specific MIME types for file uploads simplifies verification. Allow listing shifts the burden from exclusion to inclusion, dramatically reducing uncertainty. Even complex fields like email addresses or URLs can rely on standardized pattern libraries that define validity precisely. By controlling the acceptable set, developers narrow the battlefield and prevent unseen patterns from becoming silent threats. Canonicalization, the process of reducing input to a single, standard form, must occur before validation or comparison. Attackers often disguise malicious content through encoding tricks, alternate path representations, or Unicode variations. Without canonicalization, a validation routine might pass a disguised payload it cannot recognize. For example, a file path containing mixed slashes or encoded dots may bypass directory checks. Normalizing input ensures comparisons and filters operate on true representations, not illusions. This step turns ambiguity into clarity. Canonicalization first, validation second, that order anchors dependable checks across every layer of a system. Validation must always happen on the server side, even if the client performs preliminary checks. Client-side controls enhance usability but cannot be trusted, since attackers can bypass browsers or modify payloads directly. The server enforces the final say, applying identical or stricter rules to all inbound data. For instance, a mobile app may restrict field length locally, but the server must revalidate before committing to a database. Server-side enforcement guarantees that logic holds regardless of user device or intent. Security belongs where control exists, on systems the organization governs, not those it cannot. Parameterized queries eliminate injection by separating data from executable instructions. In database operations, user input should never concatenate directly into command strings. Parameters treat inputs strictly as data, allowing the query engine to handle substitution safely. For example, an SQL statement using placeholders prevents attackers from inserting commands like drop table through a text field. The same principle applies to operating system calls and search templates. Parameterization transforms untrusted text into inert content. It is one of the simplest, most effective countermeasures in secure coding, an enduring rule that every developer must follow. Strict parsing for file uploads ensures that what enters the system is truly what it claims to be. File headers, MIME types, and content signatures must align with expectations. For instance, if a user uploads an image, the server should confirm the file's magic bytes and dimensions match its declared type. Reject archives containing executables disguised under benign extensions, and limit decomposition depth to avoid resource exhaustion. Validating structure before acceptance protects not only storage but also downstream processors. Files should never be trusted merely because their names look safe. A parser's skepticism preserves system integrity. Failing closed with informative errors prevents both exploitation and confusion. When validation fails, the system should reject input firmly but clearly, explaining the issue in user-safe terms without revealing internal logic. For example, reporting invalid format is better than exposing the exact validation rule or code path. Failing closed ensures no partial execution occurs with bad data. Informative messaging guides legitimate users to correction while keeping attackers guessing. Combined, these practices prevent small errors from turning into gateway flaws. Strong rejections protect the system while maintaining user experience and operational transparency. Logging validation failures with context provides early warning of attack patterns and design gaps. Each failed attempt should record timestamp, source, target field, and reason for failure, without storing dangerous payloads verbatim. Aggregating this data reveals repeated probing or common user misunderstandings. For instance, a spike in invalid input attempts on a specific endpoint could indicate active testing by a malicious actor. Monitoring these signals transforms validation from passive defense into active intelligence. Logged evidence also aids forensic reconstruction after incidents, bridging the gap between prevention and analysis. Fuzz testing critical interfaces before release uncovers hidden vulnerabilities by bombarding inputs with random or malformed data. Fuzzing exposes how applications handle unexpected edge cases, from memory errors to logic flaws. For example, fuzzing an API endpoint may reveal that certain characters crash the service or bypass input filters. Integrating fuzz tests into continuous integration pipelines ensures that each new build inherits resilience. This proactive exercise mimics adversary experimentation safely. By failing in the lab instead of in production, systems learn where their limits lie and strengthen before facing real hostility. Third-party libraries that perform validation must be pinned to verified versions and vetted for integrity. Open-source components save time, but can inherit vulnerabilities from past or unmaintained releases. Pinning fixes dependency drift. Verification through checksums or signatures ensures authenticity. For instance, validating that a JSON parser comes from the official repository and matches its published hash protects against supply chain tampering. Dependency hygiene is as vital as code hygiene. Trust in borrowed logic must rest on evidence, not assumption, especially when that logic decides what data your systems will accept. Metrics finally make validation measurable through rejection rates and defect escape counts. Rejection rate shows how often the system blocks unsafe or malformed input. Defect escapes measure how many validation-related bugs reach production. Tracking these metrics over time reveals whether filters are too lax or overly strict. For example, rising escape rates may signal new attack methods, while falling rejections could suggest validation drift. Quantifying behavior turns craftsmanship into accountability. With numbers in hand, teams tune validation scientifically rather than by instinct, ensuring protection evolves as fast as threats. In conclusion, Control SI-10 embeds validation as a permanent design habit. Every interface, protocol, and workflow must assume adversarial input and prove data safety before trust. Proper validation blends technical rigor with consistency checking type, encoding, and context every time. Systems that practice these disciplines avoid many of the most common and costly vulnerabilities in modern computing. Input validation is not decoration, it is defense at the molecular level of information flow. When done habitually and precisely, it transforms hostile environments into predictable, manageable systems worthy of trust. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.